Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. The Multiverse Hypothesis. An Odyssey through infinite realms. The multiverse hypothesis is one of the most intriguing and speculative ideas in modern science. It challenges our understanding of reality, suggesting that our universe is not unique but rather one of countless others. To understand this concept fully, we must journey through the realms of cosmology, quantum mechanics, and theoretical physics. The concept of the multiverse has ancient roots. Early Greek philosophers like Democritus speculated about the existence of other worlds. They imagined an infinite cosmos teeming with a multitude of worlds, each differing in size, shape, and composition. However, these ideas were largely philosophical and lacked empirical grounding. It wasn't until the 20th century, with the advent of quantum mechanics and modern cosmology, that the multiverse hypothesis gained scientific traction. Quantum mechanics, the science of the very small, provided the first solid footing for the multiverse hypothesis. In the early 1900s, experiments revealed that particles such as electrons could exhibit wave-like behavior, leading to the development of the wave-particle duality concept. The double-slit experiment, in particular, demonstrated that particles could exist in a superposition of states, behaving as both particles and waves until measured. This led to the Copenhagen interpretation of quantum mechanics, proposed by Niels Bohr, which posited that particles exist in multiple states simultaneously and only collapse into a single state upon observation. While the Copenhagen interpretation became widely accepted, it raised profound questions about the nature of reality. What happens to the other possible outcomes when a quantum event is observed? Enter Hugh Everett III, a Princeton University graduate student in the 1950s. Everett proposed the many worlds interpretation, MWI, of quantum mechanics. According to Everett, all possible outcomes of quantum measurements actually occur, each in its own separate universe. In other words, every time a quantum event takes place, the universe splits into multiple branches, each representing a different outcome. This radical idea suggested that our universe is part of an ever-growing tree of diverging realities, each as real as the next. Everett's theory initially faced skepticism and ridicule. The notion of an infinite number of universes, each slightly different, was too much for many to accept. Yet, as quantum mechanics continued to produce inexplicable results, the many worlds interpretation gained a foothold among a small group of physicists. It offered a way to explain the bizarre behavior of particles without invoking the observer effect, where observation itself is believed to alter the outcome of an experiment. While quantum mechanics laid the groundwork for the multiverse hypothesis, cosmology provided another pathway to parallel universes. In the 1980s, Alan Gough's theory of cosmic inflation revolutionized our understanding of the early universe. According to Gough, the universe underwent a rapid expansion shortly after the Big Bang, stretching spacetime to astronomical proportions in a fraction of a second. This theory elegantly explained the uniformity of the cosmic microwave background radiation and the large-scale structure of the universe. However, cosmic inflation also implied the existence of other regions of space that underwent their own inflationary periods. These regions, or bubble universes, could be entirely separate from our own, with different physical laws and constants. Thus, the concept of a multiverse consisting of an infinite number of bubble universes emerged from the study of cosmic inflation. String theory, another significant development in theoretical physics, further bolstered the multiverse hypothesis. String theory posits that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings can vibrate at different frequencies, giving rise to the various particles and forces in the universe. String theory requires the existence of additional spatial dimensions beyond the familiar three. These extra dimensions are compactified, or curled up, in such a way that they are not directly observable. String theory also introduced the idea of a vast landscape of possible universes. Each universe in this landscape corresponds to a different way of compactifying the extra dimensions, leading to different physical laws and constants. Some physicists, like Leonard Susskind, argue that the landscape could explain why our universe appears fine-tuned for life. In a multiverse of countless possibilities, it is not surprising that at least one universe has the right conditions for life to arise. The anthropic principle adds another layer to the multiverse hypothesis. Proposed by Brandon Carter in the 1970s, the anthropic principle suggests that the fundamental parameters of the universe must allow for the existence of observers, because we are here to observe them. In a multiverse, this principle implies that we find ourselves in a universe with just the right conditions for life because only such universes can have observers. This idea has been both celebrated and criticized. Critics argue that the anthropic principle is a tautology that explains nothing and avoids addressing deeper questions about the nature of reality. Supporters, however, see it as a logical consequence of the multiverse hypothesis, providing a framework to understand why our universe appears so finely tuned. Quantum cosmology, the study of the universe's origin using quantum mechanics, further supports the multiverse hypothesis. According to some theories, the universe could have originated from a quantum fluctuation in a primordial vacuum. If such fluctuations are possible, they could give rise to multiple universes, each emerging from its own fluctuation. The concept of eternal inflation, proposed by physicist Andre Linde, builds on Guth's inflationary theory. Linde suggested that inflation is not a one-time event but an ongoing process. As inflationary regions expand, they give birth to new regions where inflation continues. This process can create an infinite number of bubble universes, each with its own distinct properties. Eternal inflation thus provides a mechanism for the continuous creation of new universes within the multiverse. One of the biggest challenges for the multiverse hypothesis is finding empirical evidence. By definition, Other universes are separate from our own and may be fundamentally unobservable. However, some scientists argue that certain phenomena could provide indirect evidence. For example, collisions between bubble universes during their formation might leave imprints on the cosmic microwave background. These imprints could manifest as unusual patterns or anomalies. Additionally, the landscape of string theory predicts a multitude of possible universes, and observing certain patterns in particle physics experiments might support the idea of a multiverse. The discovery of dark energy, a mysterious force driving the accelerated expansion of the universe, has also spurred interest in the multiverse. Some theories suggest that dark energy could be a manifestation of interactions with other universes. Understanding the nature of dark energy might provide clues about the existence of the multiverse. The multiverse hypothesis has profound philosophical implications, challenging our understanding of reality, causality, and our place in the cosmos. If the multiverse exists, then every possible history and future exists in some universe. This raises questions about the nature of free will and the meaning of existence. Some philosophers argue that the multiverse undermines the uniqueness of our experiences. If every possible outcome is realized in some universe, then our decisions might feel less significant. Others counter that the multiverse enriches our understanding of reality, showing that our universe is just one of many possible expressions of the cosmos. Despite the challenges, researchers continue to seek evidence for the multiverse. Advances in cosmology, quantum mechanics, and particle physics offer new avenues for exploration. Scientists are looking for signs of other universes in the cosmic microwave background, conducting experiments at particle accelerators, and developing new theoretical models. One promising approach involves searching for anomalies in the cosmic microwave background, CMB, the afterglow of the Big Bang. The CMB provides a snapshot of the early universe, and any irregularities could hint at interactions with other universes. For instance, if our bubble universe collided with another during its formation, it might leave detectable signatures in the CMB, such as unusual temperature fluctuations or patterns. Particle physics experiments, particularly those conducted at the Large Hadron Collider, LHC, might also provide clues about the multiverse. By smashing particles together at incredibly high energies, physicists hope to recreate conditions similar to those just after the Big Bang. These experiments could reveal new particles or forces that hint at the existence of extra dimensions or other universes. For example, the detection of many black holes or deviations from the standard model of particle physics could suggest the presence of parallel universes. Moreover, the study of dark matter and dark energy, which together make up about 95% of the universe's total mass energy content, might offer insights into the multiverse. Dark matter, which exerts gravitational effects but does not interact with light, could consist of particles that originate from other universes. Similarly, dark energy, responsible for the accelerated expansion of the universe, might be influenced by interactions with parallel universes. Theoretical developments also play a crucial role in the search for evidence. physicists are refining models of cosmic inflation and string theory to make more precise predictions about the multiverse. These models help guide experimental efforts and suggest new ways to test the hypothesis. For instance, some versions of string theory predict the existence of certain types of particles or forces that could be detected in future experiments. While the multiverse hypothesis remains speculative, its implications are profound. It challenges our understanding of reality, suggesting that our universe is just one of many, each with its own unique properties. This idea forces us to reconsider fundamental concepts such as causality, free will, and the nature of existence. It also opens up new avenues of scientific inquiry, pushing the boundaries of what we can observe and measure. If the multiverse hypothesis is correct, it means that every possible history and future exists in some universe. In one universe, the dinosaurs might never have gone extinct, while in another, humans might have colonized other galaxies. The possibilities are endless, and each universe offers a different perspective on reality. The multiverse hypothesis also has profound philosophical implications. It challenges the notion of a single, unique reality and suggests that our experiences are just one of many possible outcomes. This idea can be both exhilarating and unsettling, as it forces us to confront the vastness of possibilities and the relative insignificance of our own experiences. Some philosophers argue that if every possible outcome is realized in some universe, then our decisions might feel less significant. However, others counter that the multiverse enriches our understanding of reality, showing that our universe is just one of many possible expressions of the cosmos. It suggests a form of cosmic democracy where all possibilities have a place. The implications for free will and determinism are equally profound. If every decision we make leads to a branching of universes, then in some sense, all choices are made. This view could imply that free will is an illusion, as every possible action is realized somewhere in the multiverse. Yet, it also suggests that we live in a universe where a particular set of choices has led to this specific reality, giving our decisions a unique significance within our own universe. Moreover, the multiverse hypothesis intersects with ideas of cosmological fine-tuning. Many physicists and cosmologists have noted that the fundamental constants of nature appear to be finely tuned to allow the existence of life. Even slight variations in these constants could result in a universe incapable of supporting life as we know it. The multiverse offers an explanation for this apparent fine-tuning. In a vast multiverse with countless universes, it is not surprising that at least one universe has the right conditions for life to arise. This is the essence of the anthropic principle, which states that we observe the universe to be life-friendly because only in such a universe could observers like us exist. This anthropic reasoning has been both lauded and criticized. Critics argue that it does not offer a testable prediction and thus falls outside the realm of empirical science. Proponents, however, view it as a natural consequence of the multiverse framework, providing a context for understanding why our universe has the properties it does. It shifts the question from why is our universe fine-tuned for life, to why do we find ourselves in a universe that supports life? The answer becomes self-evident within the multiverse context. The multiverse hypothesis also intersects with the concept of eternal inflation, an extension of the inflationary model of the universe. Inflation theory, proposed by Alan Guth and later refined by Andre Linde and others, suggests that the universe underwent a rapid exponential expansion in its earliest moments. Linde's notion of eternal inflation posits that this inflationary process never completely ends. Instead, while inflation stops in some regions, leading to the formation of bubble universes like ours, it continues in other regions. This ongoing inflation process can create an infinite number of bubble universes, each with its own distinct properties and physical laws. Eternal inflation thus provides a mechanism for generating a multiverse, where each bubble universe could have different characteristics depending on the local conditions when inflation ended. This model aligns well with the idea of a vast and varied multiverse, where each bubble universe is like a separate room in an infinitely large mansion. The walls of these rooms might be insurmountable, making it difficult or impossible to interact with other bubble universes directly. Despite the challenges in obtaining direct evidence, some scientists believe that we might detect indirect signs of other universes. One proposed method involves searching for bruises on our universe, subtle imprints left by collisions with other bubble universes in the early moments after inflation. These collisions could create detectable anomalies in the cosmic microwave background, CMB, the afterglow of the Big Bang that pervades the universe. Researchers are meticulously analyzing the CMB for any irregularities that could hint at such collisions, though none have been definitively found so far. Another avenue for potential evidence lies in the realm of particle physics. High-energy collisions, such as those conducted at the Large Hadron Collider, LHC, could produce new particles or reveal deviations from the standard model that suggest the existence of extra dimensions or parallel universes. For example, the detection of many black holes at energy levels achievable at the LHC could provide evidence for extra dimensions predicted by certain string theory models. Such discoveries would bolster the case for the multiverse by suggesting that our universe is part of a larger, more complex reality. Theoretical physicists are also exploring the implications of the multiverse for fundamental questions in physics. Some theories suggest that the constants of nature, such as the strength of gravity or the mass of the electron, might vary from one universe to another within the multiverse. If true, this could explain why these constants seem fine-tuned for life in our universe. We exist in one of the rare universes where the conditions are right for life to emerge. This perspective offers a potential solution to the problem of fine-tuning, though it remains speculative without empirical verification. In addition to these scientific inquiries, the multiverse hypothesis has inspired a wealth of creative and philosophical exploration. It has become a popular theme in science fiction, where writers and filmmakers imagine worlds where every decision creates a new branch of reality, leading to infinite parallel universes with wildly different outcomes. These stories capture the imagination and highlight the profound and often unsettling implications of the multiverse. the multiverse hypothesis challenges us to rethink our place in the cosmos. It suggests that our universe is not the center of everything, but rather a tiny part of a vast and diverse multiverse. This perspective can be both humbling and exhilarating, as it expands our horizons and encourages us to explore the deepest questions about the nature of reality. In conclusion, the multiverse hypothesis represents one of the most daring and profound ideas in modern science. It challenges our understanding of reality, suggesting that our universe is just one of countless others, each with its own unique properties and laws. While empirical evidence remains elusive, the concept continues to inspire new theories and experiments, pushing the boundaries of what we can observe and measure. Whether or not we ever find definitive proof of other universes, the journey to understand the multiverse is a testament to human curiosity and our relentless pursuit of knowledge. The multiverse hypothesis invites us to consider the possibility that reality is far more complex and wondrous than we ever imagined. It encourages us to keep exploring, questioning, and expanding our understanding of the cosmos. In the end, the pursuit of the multiverse is not just about discovering other universes. It's about deepening our understanding of the universe we inhabit and our place within it. As we continue this journey, we may find that the multiverse, with all its infinite possibilities, is a reflection of the boundless curiosity and creativity that drives us to seek answers to the most profound questions of existence.